Hello class. Well, this lesson is my last try in order to explain to you, in order to make sense of the symbols a to the 0 and a to the -1. So basically, I put all of the ideas together, all of the ideas that I have been telling you about, in order with some language that I think is going to be very precise. And so let's follow each of these, let's say, chapters. Okay, so let's start. What is the first chapter in this lesson? Chapter 1. The need for the creation of exponent notation. So when we encounter something like this in mathematics, guys, a product, which is basically the product of equal factors, you see, all the factors are the same number. People realized that this is too long to write. It takes a lot of space. And then they thought, or they asked themselves, why don't we create a shorthand notation to represent a product whose factors are all equal, like this product, right? So they asked themselves this question, because mathematicians are always trying to make all the writing as economical as possible. And somebody said, why don't we write the symbol 2 and then a little 10 on top, on the corner? Why don't we write this symbol to represent the product of 10 factors? There it is, 10, all equal to 2. There it is. And people agreed with this symbology to represent something like this. Or if they had something like this, 4 times 4 times 4 times 4, 4 times 4, then they agreed to represent all of this as 4 and then a 5 on top. So this is basically the factor that you're going to multiply by itself, and this is the number of times you're going to multiply it by itself. Very simple idea. And it makes sense, right? It makes sense to try to economize our writing. Perfect. That's chapter 1. Chapter 2. The precise definition of the symbol a to the x. So after we start thinking of a new mathematical concept or object, we next need to define it with extreme precision, guys. In here, these were the first steps towards the concept of exponent and base. All right. At this point, people were making like tiny steps towards the formalization of a concept. Now that you have been doing all of this stuff during a few days or weeks or months, then comes the time in which you need to define your concept. In this case, this concept, right, or this new symbol, you need to define it with extreme precision. That's always the case in mathematics. You need to define every new object, every new mathematical concept. Once you have thought about it, next you need to define it with extreme precision. And therefore, these people said, definition. For any number a and any positive integer x, we define the symbol a to the x as this. A to the x is going to be exactly equal to a times a times a times a, etc. times a. How many times? X times. As many times as the exponent tells you. And by the way, they also baptized, or they also gave name to this number. They called it the base, and they called this one the exponent. You see, so this is a very clear and precise definition. Why the need to include this restriction, guys? Why the need to say that x must be a positive integer? Well, because what I have been telling you, given this idea in here, then we can, at this point in our debate or discourse, in our learning, we cannot say we cannot talk about something like this. Well, I'm gonna use the number 2 as an example. If I write this, if I permit the exponent to be 0, then what I would be saying is that I want to multiply 2 by itself how many times? 0 times. And I don't know what that means, guys. I don't know what it means. No one knew what it means to multiply a number by itself 0 times. It didn't make sense. And if this doesn't make sense, this is even worse. Something like this. 2 to the minus 2 or 2 to the minus 1, any negative integer. Why? Because what does it mean to multiply 2 by itself minus 1 times? What in the world could that mean? You see, that's why we need to restrict the x to be a positive integer to make sense of this concept that we have in mind. That's why. So this is a precise definition, and we need to respect it in the future. We need to respect that definition. Fine. Chapter number 3. The realization that writing a to the 0 or a to the minus 1 does not have any meaning at this point. I mean, this is pretty much the same I already told you a few seconds ago. A to the 0 and a to the minus 1 does not have meaning for the same reason I told you here. So let's see. In mathematics, the fact that we can write any string of symbols does not mean that such a string has meaning. For example, you can write this in your notebook, 3 plus equals 2. But the fact that you can write it, guys, does not mean that this string of symbols has meaning. This is meaningless. Can you assign meaning to this? Can you make sense of this symbol, of this symbology? Clearly not. The same with 1 over 0. We can write it down. That doesn't mean that this has meaning. We cannot do this, guys. We don't know what this means. What does it mean to multiply x to the square times infinite? I don't know what this means, because I know how to multiply numbers by numbers, but I don't know what it means to multiply numbers by an infinite. The infinite is not a number. So what could this possibly mean? Sure, I can write it down. That doesn't mean that this thing has meaning. I can write the symbol, a variable x, and then a little arrow pointing upwards here in the corner. What does this mean, guys? I can write it, but that doesn't mean that this thing is meaningful. You see? So therefore, what can we conclude out of this? That at this point, even though we can write this symbol, a to the 0 or a to the minus 1, these things have no meaning. Why not? Because they don't respect my definition. You see? In order for me to write something like this, a to the x or something, then x must respect the fact that it has to be positive integer. There is no problem with a. A can be any number. That's okay, but not x. X has to be a positive integer. So in short, we can just say that these objects don't exist. This object does not exist at this point, and this object does not exist. All right, so that's the closure of the chapter number 3. Let me make a pause, and I'll be back with you in a moment. Let's continue with chapter 4. So chapter 4. Now we can build a mathematical structure or theory with what we have at this point. For example, we can demonstrate the following statements, also known as laws. So basically, guys, all of these things that we have been calling laws are basically statements, right? Because a statement is something that you are affirming, right? In this case, in the first one, my statement is that I affirm that a to the x times a to the y is equal to a to the x plus y. That's a statement. And we need to demonstrate it like we did before. I'm not going to do the demonstration, but you must remember that one. Okay, notice the following, guys. This statement is completely meaningful. All of this statement. I can start to demonstrate this because every single symbol is meaningful for us if we keep restricting ourselves to x and y being positive integers. You see, All of these things have meaning. In this law, nevertheless, we need to make a restriction, right? A to the x over a to the y is equal to a to the x minus y, but as long as x is greater than y. Because if that's not the case, in here we can encounter, once again, 0 or negative integers, and we don't want that, because at this point that is meaningless. Okay, but if somebody said, guys, hey, I have a proof that a to the 0 is equal to 1. This is, I mean, you don't even have to hear anything else. If a person says, I can demonstrate that a to the 0 equals 1, you need to stop this person right there and ask him, what do you mean by a to the 0? Because according to our definition, this thing doesn't even exist. So how can you affirm that this object, which doesn't exist, is equal to 1? It's meaningless. You see, this is not a demonstration. That's what I've been telling you. It cannot be a demonstration. I cannot demonstrate anything about a concept that I don't even know what it means. Chapter 5. The realization that it would be nice to have meaning for the symbol a to the 0 and the symbol a to the minus 1, or a to any other negative integer. It would be very nice to have meaning for this and this. Why? Why do I say this? Because of the following, guys. It would be nice to have a more general theory of exponents and not discriminate, so to speak, against exponents equal to 0 or negative integers as exponents. You see? Why? Because any mathematical theory, the more general that it can be, the better. We don't like restrictions in mathematics. If we can make something as general as possible, that's always a great idea. Okay, that's the first thing. It's because it would be nice to have a more general theory of exponents and not just work with positive integers as exponents. And the second thing, guys, and I think this is even more meaningful, is that even some practical applications prompt us or lead us into wanting to define this symbol, a to the 0. What practical applications am I talking about? You must remember that we have already dealt with this idea of the binary fission by bacteria, right? And at some point we perform this problem, something like this. We assume that we have a bacterium at time 0, okay? And then let's suppose that this bacterium divides into 2 bacteria after 1 minute. So at time 1 minute, we're gonna have 2 bacteria. And then another minute goes by, minute 2, and this will divide into 2 respectively, and now we will have 4 bacteria at time 2. And at time 3, we're gonna get 8 bacteria, and so on. We could go on like this. Now, suppose that I want to write the number of bacteria n. Let's suppose n represents the number of bacteria in this hypothetical experiment. Let's suppose n represents the number of bacteria, and we want to write n in terms of the time t. In terms of t, the time. We may write the following formula. N equals 2 raised to the t. Why do I write this? Because when t is equal, for example, to 1, okay, if I gave the value of 1 to t, then what am I gonna get? 2 to the 1, that's 2. Now, does this confirm what I have in here? Yes. At time 1, we have 2 bacteria, which is right here. You see, the same is gonna happen for the next time. At time 2, there it is, time 2. How many bacteria do we have? 2 to the 2, that's 4. Does that coincide with what we have here? Yes. At time 2, we have 4 bacteria. And so on, for the 3rd minute, and so on. The only problem, guys, the only problem is that you cannot go backwards. I mean, this formula makes sense from this point downwards. You see, because 2 to the 0, okay, like which would account for this first step, 2 raised to the times 0 this time, has no meaning for us. This object has no meaning for us, even though this experiment is kind of telling me that according to this pattern, according to this formula, then 2 to the 0 should be equal to 1 bacteria. Well, the number of bacteria at time 0 should be 1 according to this. At time 0, we should have 1 bacteria. I cannot write this down because according to our theory, this has no meaning. You see the problem, guys. There is this application that is telling me that it would be very nice to have a definition for this, and at this point we have suspicion that if the symbol a to the 0 could mean anything, it better be 1 because of this experiment. You see, we are suspecting that any number raised to the 0, in this case it was 2, but it could be any other number, any number raised to the 0 must be 1. You see my point? This is just a suspicion, but at this point, once again, this symbol has no meaning. Another stop, and I'll be back with you. And finally, chapter number 6, we have the following, guys. This is the last chapter in this story, and the most difficult. So let's see. So finally, we can decide to give meaning to the symbols a to the 0 and a to the -1. Why? Because that would be a very good idea to make my theory of exponents more general, and because some applications actually make me feel that we have to define these two things, right? Like the previous example about the bacteria. Something in the air tells me that I should define these two things. Okay, so we do this by trying to assign meaning to a to the 0 and a to the -1 in such a way so as to respect all the structure that we have been building. This is the key idea. What structure am I talking about? This structure, guys, the laws of exponents that we have already demonstrated, but only in the case that x and y are positive integers. And in particular, for this law, we have another restriction. We need x and y not only to be positive integers, but also we need x to be specifically greater than y. Because if this is not the case, if x could be equal to y, then in here it's going to appear a 0, which we don't want at this point. And if x was less than y, this would be a negative integer, which at this point also makes no sense. So I want to define this symbol and this symbol so that these laws are also valid for any exponent. Any exponent. Positive exponents, 0 exponents, and negative exponents. Alright, so how do we do this? How do we assign meaning to this and this in such a way so as to respect all of this, or in such a way so that these definitions for these objects are in harmony with all of this previous structure? What we do is the following. We assume that the previous laws are valid for any integer x and any integer y. Any integer x and any integer y. I'm going to assume that all of these laws are valid for any integer, whether it's positive, negative, or 0. By the way, the 0 is an integer. And therefore, once I make that assumption, we observe what this assumption can tell us about the possible meaning or the possible nature of the symbol a to the 0 and a to the -1. And I'm gonna do this now by hand because I think it's enlightening. So let's pick this first, this law first, which is this one, and it's being restrictive. But remember, now we're gonna assume that this law holds for any integer. So I'm gonna discard this restriction now. So let's suppose that this law is valid for any x, any integer x, and any integer y. I should have written integer, but I mean, I'm just pronouncing it. Okay, so if that's the case, if I make that assumption, then I can make y equal to x, something which in this case was not allowed. In this case, I can do it. So let's do it. I'm gonna make the y equal to x, and I'm gonna have this. Therefore, according to this law, this fraction should be equal to this, right? And then clearly a to this exponent is the same as a to the 0, right? X minus x is going to be 0. Okay, and we also can go a little backwards, so to speak, or I mean, we can also make the deduction that any fraction in this form, any fraction that has the same numerator and as the denominator, in such a way that this and this are equal, we know that such a fraction should be 1 when you divide something over its same number, over the same number. So all of this chain of reasoning, or all of these nested equations, tells me that 1 is equal to a to the 0, like this. Now, is all of this a demonstration that a to the 0 is equal to 1? No, it's not a demonstration, guys. Why not? Why cannot this be a demonstration? You need to understand that we don't know at this point what this symbol means. So I cannot say that this is a demonstration of the fact that a to the 0 equals 1. It's not a demonstration. Not a demonstration. What is this then? This is just a conclusion that we obtain if we make the assumption that all of these laws are valid for any integer. And what we can do, instead of saying, okay, this is a demonstration that a to the 0 equals 1, what we can do is just say that we define a to the 0 as being equal to 1. Why? Because if I do that, then the definition of this symbol will be in accordance, or will be in harmony with the previous structure. Any other way that you want to define a to the 0, let's say that you want to define a to the 0 as 2, or you want to define it as the square root of 3, or any other possible definition that you can give to this number, will not be in harmony with all of this, because of this reasoning that I'm saying. You see? So this is the right statement, guys. We define a to the 0 as being equal to 1, so that it's in accordance with all of the previous structure, which means that it's in harmony. That's it, but it's not a definition. I'm sorry, it's not a demonstration. You see, that's how it works. I know that this is extremely subtle. The difference between understanding this as a definition and not a demonstration is extremely subtle. Es muy sutil y difícil de entender. So don't be anxious if you don't get it completely. It's fine. It's fine, guys. Don't worry. I definitely did not understand this in high school. Definitely. I was not even told that this thing was possible to do. Okay, so now we already defined a to the 0 as being equal to 1, so that definition respects all of the previous structure that we have been building. And this is what we mean by the structure, all the laws concerning the exponents. And we can do the same, guys, for a to the minus 1. For a to the minus 1, I can choose this law. All right. At this point, this law, remember, this law is only valid for x and y being positive integers. But let's assume one more time that that law holds for any possible x and y. So this is true for any integer x and any integer y. Let's assume that. Okay, what conclusion can that bring? Well, let's see. If x and y can be any integer, then I can decide that y is equal to minus x. I'm gonna make y equals to minus x, like this. And according to this law, this should be equal to a raised to the x minus x. It's just the addition of the exponents, right? And a to the x minus x is a to the 0, which we have already defined as 1. Can you see? We are already using the previous definition, guys. It's kind of like building, a building, right? Constructing a building. I base my reasonings on the top. All of this reasoning is based on the previous reasoning, which is based on previous reasonings, and so on. That's how mathematics is built. It's built upwards in that way. So, okay, let's go back here. I don't want to lose you. So basically, all of these nested equations tells me that this is equal to 1. So let's just write that part in here. Like that. And then I can isolate this symbol, a to the minus x, by simply dividing both sides over a to the x, right? And that's it, guys. This is the conclusion. The conclusion is that if I want this law to be valid for any x and any y, any possible integer x and any possible integer y, then the conclusion is that a to the minus x should be equal to 1 over a to the x. Once again, is this a demonstration that this symbol is equal to this? No, it's not a demonstration, because at this point in my discourse, I don't know what this means. This is just a possible conclusion that we can extract by the assumption that this law should be valid for all integers. And what we can do is just say, okay, let's define a to the minus x as 1 over a to the x. Because if I do this, if I make this definition, then this definition will be in accordance with all of the previous structure. Any other way that you want to define this symbol, a to the minus x, will bring cracks or will not be in harmony with all of this structure. You see, that's why we define the symbol to be equal to this. But it's not a demonstration, it's a definition. We just say it is. And that's it, guys. That's the end of the story. Let me go back with you because I still have some stuff to say.